Alright guys, hello. So in one of my videos I talked about moments of a force, and in this video we're going to do some questions specifically about moments in different scenarios to give you a good understanding. Now firstly we have this diagram here. You can observe all the dimensions and quantities. We have a hinge here at A, we have the weight of the computer, upward force acting at B, the distances. So let's go. First one says calculate the weight of the tabletop. Now in the question up here, it says that the tabletop has a mass of 5 kilograms. So we know that weight is equal to mass times g, i.e. gravity with the acceleration. So it's equal to 5 kg times 9.8 newtons per kilogram. Of course, per kilogram cancels out kilogram, and so we are left with 5 times 9.8, which gives us 49 newtons. So of course we know that the weight of the desktop is 49 newtons. Next one says draw and label the arrow representing the weight of the tabletop. Now of course the weight of the tabletop would be somewhere roughly in the middle and would be acting downward, so we could probably draw it here and draw that downward first and write 49 newtons inside it. Now the final part here says apply the principle of moment about the hinge at A to determine the vertical force F applied at B that is required to maintain tabletop in equilibrium. So now what we need to do is we need to look at which moments are going in one direction, which ones are going in the other direction. So what you'll notice is that the force F is going in this direction, going in the anti-clockwise direction, pushing this thing in the anti-clockwise direction. Meanwhile, the forces of the weight of the computer and weight of the table are pushing it in the other direction. So we can say that 0.8 times the force F, we'll say it's x newtons, is equal to the 200 newtons of the computer, that's the weight of the computer, multiplied by the 0.25 meters. And please remember, we're taking moments from the hinge here, from the hinge, so we're taking distances from where the hinge is. That's where we're getting these distance values from. And then of course we're adding that to the 49 newtons, that's the weight of the desk, multiplied by, it says up here that it's 0.4 meters away from the axis at the hinge, multiplied by 0.4. So we can just go ahead and punch this into the calculator. 200 times 0.25 plus 49 times 0.4, and we get 0.8 times x newtons is equivalent to 69.6 Newton meters. Now we can transpose and say that x newtons is equal to 69.6 Newton meters divided by 0.8 meters. Meters cancels meters, and dividing this, we get precisely 87 newtons. So the force acting here is 87 newtons. Let's move on to the next question. Here we have a diagram that shows the open bonnet of a car. The bonnet is held at the angle of 60 degrees to the horizontal by a vertical force V at one end of the bonnet. The bonnet is 0.9 meters long and has a weight of 25 newtons. And the center of gravity G is 0.35 meters from the hinge at O. So first thing, draw and label the two forces other than V acting on the bonnet. Now, one of them is at G, the center of gravity, and that would be acting downwards. Yeah? Since the weight is 25 newtons, then that would be acting downward with 25 newtons. And the other one is the horizontal component of this force. Let me draw this with a perfectly straight line. So the other force would be the horizontal component that's acting upwards this way. So those are the other two forces acting on it, one at G and one at O. Now the next one says, by taking moments at O, or about O, show that the vertical force V applied at the end of the bonnet is 9.5 newtons. So we're taking at O, and now we're gonna look at the two other forces, G and V. V is in one direction and G is in another direction. So we can say that V times 0.9, since that's the distance of it from O, multiplied by cosine 60, and we're multiplying it by cosine 60 because we are resolving the vector. As we see that there's a horizontal component, and we're resolving the horizontal component of the vector that's going in this direction. So that's why we multiply it by cos 60. Then we're going to say that is equal to the weight, 25 newtons, times 0.35. That's the distance that the weight center of gravity is from the O, 0.35, also multiplied by cos 60. Okay, now first thing we can do, we can go ahead and punch these into our calculator. The right hand side where we have all the values, and we get V times 0.9 times cosine 60 is equivalent to 375. And now we can multiply 0.9 times cosine 60, and we'll get 0.45. So we'll get V is now equal to 4.375 divided by 0.45, and we get 9.72 newtons. And if we look back here, they're asking for 9.7, so if we run to one decimal, we got the value. Now, last one says calculate the magnitude of the force acting at the hinge O. The best way to go about this is to use the principle that the sum of the upward forces must equal the sum of the downward forces. So V is acting up, O is acting up, and G is acting down. So the force at V, which we know is 9.7, plus the force at O that we don't know, call it O, equals 25 newtons at G. Therefore, 25 minus 9.7 is equivalent to O. Therefore, O is equivalent to 15.3 newtons. That will be all for today. Thanks for watching.
Tell me pretty lies, look me in the face, tell me that you love me.